Now it's time to start part 3 of the clutter rejection lecture, which is lecture 8 in the Introduction to Radar Systems course. Now, one issue I want to bring up is called sensitivity time control. And that is, it deals with the issue, and here we see a ship-based radar that's sending out a signal, and let's just assume these numbers aren't specific characteristics of any radar, but say, or any target. The pictures are just for examples, figurative examples. If we have a radar on this ship that could see a 1 square meter, that's 0 dBSM aircraft at 200 kilometers, because of just the r to the 4th dependence of the radar range equation, you could see a mosquito, which has a minus 64 dBSM cross-section, at 5 kilometers. So what that says is the radar is going to be incredibly sensitive at close ranges in order to see reasonably small-sized targets out at far ranges. And this effect was noticed the minute people built surveillance radars back in the late 40s and 50s. And what they did was they developed a technique they call sensitivity time control, whereby they attenuate the radar return by r to the minus 4 to compensate for the r to the minus 4 sensitivity of the radar, and it results in a constant signal-to-noise ratio as a function of range for a constant cross-section target. Okay? Now, sensitivity time control is great, but you can't use it if your radar's waveform is ambiguous in range, because if this radar's waveform was ambiguous in range, then I'd only have an unambiguous range interval. Say I had it only of 10 kilometers. This target down here would be way down here, so I'd be attenuating the signal strength with an r to the 4th factor, thinking it was really down here. In other words, it's saying you can't attenuate targets at 100 at very far ranges if you don't know their absolute range. You only know it ambiguously. So targets which are beyond the ambiguous range of the radar will be very strongly attenuated because they're going to be folded over or aliased down to close ranges. I alluded to this earlier, and this chart shows it up quite vividly. We classify pulse Doppler and MTI radars into 3 categories: low PRF, medium PRF, and high PRF. And we classify them in these 3 categories depending on the ambiguity of their range and velocity measurements. And with each of these different classes of radars, there are some pluses and some minuses. Low PRF radars are unambiguous in range. In other words, all the targets that you're going to want to see, unambiguously you can measure their range, but their velocity measurements are quite ambiguous. In high PRF radars, it's like Goldilocks and the 3 Bears. In high PRF radars, the range measurements are very ambiguous, but the velocity measurements, and of course these are radio velocity measurements, are unambiguous. And in medium PRF radars, both of them are ambiguous. Okay? And these are the range measurements and the velocity measurements for the ensemble of targets that you're interested in. Now, what are the issues when we have low PRF radars? With low PRF radars, because they operate at a low PRF, the pulse repetition frequencies, the wind-blown clutter can fill up a big portion of the Doppler space, and that can be a problem. And with those radars, you can use sensitivity time control because they're unambiguous in range. So that's a good thing about the low PRF radars. And airport surveillance radars that I talked about fall in this category. And in most short-range up to 100 miles, ground-based surveillance radars, typically are low PRF radars. Many of them are. Now, in high PRF radars, we have the pulse width is, we're sending out so many pulses per second that the pulse is on a significant amount of the time, and so that when the transmit is turned on, you can't see the targets. You have to be listening, and because of that, part of the time or the range extent that you can see the target is significantly impaired just by the actual pulse length, and that's called a range eclipsing loss. And also, the far out targets compete with near-in clutter. So if you have a very weak target out at far ranges and you're ambiguous in range, that very weak target is going to be competing against a very intense target. It's hard enough when the target's in close to compete with the clutter, but when the target is very weak and that makes it more difficult. Because we're ambiguous in range, we can't use STC. And literally, medium PRFs radars have all of it. They have these problems and they have these problems. Okay? And the ambiguities are the hardest to remove. And the way we remove these ambiguities is sending out bursts with different constant PRFs and comparing what cells the targets are in the different PRFs and unravel the ambiguities that way. But that takes a lot more energy. If I could do the detection process with just one coherent processing burst, that would be fine. But in order to unravel the ambiguities, I have to send out 3 or 4 sets of those pulses. That takes 3 or 4 times the power in the radar to do that, and 3 or 4 times the time available, what we call time occupancy, the time before I can go back and repeat the process of doing tracking and surveillance and all the different functions of the radar. Okay. Now this is one of the more simple ways that for a simple case we resolve, and I'm going to show you velocity ambiguities. Okay? Now say we have a coherent processing interval number 1 and a coherent processing interval number 2. And we have in real Doppler space a target up here. And this is its real Doppler. Okay? Now, in this particular case, the target is there's a velocity ambiguity because this is the PRF for the first PRF, this is the blind speed, the blind Doppler velocity. And for the second PRF, what we're doing is we're sending that out with a different pulse spacing. In this case, we'll send out, say, 10 pulses or 16 pulses at this PRF, and then 16 pulses at this PRF. And we notice that what happens is the real target, the Doppler filter that the real target falls in is n times the dot line speed plus the residue left over, halfway between the 0 and the blind speed, because all this folds down. All of these fold down. And you see it here. In the ambiguous space that you measure in, the target would appear here. Now when we transmit at a greater PRF, it folds down not 1, 2, 3, 4 times in a residue, but 1, 2, 3 times in a residue. But the residue is higher, in the residue of Doppler space, so it falls here. Okay, and from looking at the different, this difference of where the target appears, what one can do is one can unravel this to find out what the real Doppler velocity of the target was. Because we know if the real target velocity was down in this, and it was unambiguous, it would show up in the same Doppler bin in each case. And it would be in a different bin if it was the real Doppler velocity was here. and consequently. So what you do is you split the entire set of pulses you have up, that you can see the target, into multiple CPIs at different PRFs. In this case, we've split it up into two CPIs. And what the blinds, it moves the blind velocities to ensure detection of all non-zero velocity targets. And you look for the correlation for where things should be. And you choose these PRFs so that the least common multiple occurs above the desired maximum unambiguous velocity. Now, this is a case where it's relatively easy to unravel because the maximum unambiguous velocity for an airport surveillance radar, you use two PRFs, and you've got enough so that it takes you up to pretty much what jet planes go that are commercial. So you can unravel those velocities pretty well. What happens if you can't? What happens if your range Doppler space is confined so that you have to send out 3 or 4 PRFs? And it's not something that you can do intuitively. You have to do it quickly in a computer. Turns out there is a thing called the Chinese remainder theorem. It's a mathematical theorem, and that is used to unravel these velocities beyond the scope of this course. And in the more advanced course, I use it with a relatively simple analogy to unravel an ambiguity problem that's sort of from the common world. And if you see if I develop that course, the advanced course in the Doppler processing section, we'll spend about 10 or 12 minutes going over that particular implementation of the Chinese remainder theorem, so that it gives you a good intuitive feeling of how it works. But it's beyond the scope of this. Suffice it to say, you can do it for much more complicated cases than just this 2 PRF scheme when you have 3 or 4 or 5 PRFs. Okay, now we're going to look very quickly at airborne radars and just some of the issues related to clutter in airborne radars. Here we have a whole set of different, they're all military radars. And we have, I think, 3 fighter aircraft. And I just want to point out that in the nose of each one of these fighter aircraft are radars. And because of this, just the size of the nose, if a man is 6 feet tall, you can expect that the aperture in these radars is pretty small. And for what you've learned about antennas already, that means the frequencies have to be relatively high to get good beam width. So in these noses are radars that assist the pilot in seeing targets in front of them. Here is the E2C, which is an aircraft which has a radar in this radome. The APS 125 is the radar in this radome of this aircraft, and the function here is these aircraft fly. They're mounted, they're based on aircraft carriers, and they fly above aircraft carriers to see aircraft that or any objects that might be coming out and threatening the fleet. Here we have AWACS, which has a large radar and a radome on its top that does surveillance of the air from, this is a KC-135, so up 35,000 feet or so. And here is the Joint Stars E8A aircraft, which has in this pod down here an APY-3 ground surveillance radar. That was used in the first Gulf War. It was written up in Aviation Week that it was rushed out there when it was in its final stages of development testing, and did some amazing ground surveillance photographs of, not photographs, but data collection of what was going on real time in the battlefield. And those pictures were pretty amazing that were in Aviation Week back in the early 1990s, right after the Gulf War. So there are a lot of radars that are mounted in airplanes. What's so different about airborne radars? Well, you've got a platform that the radar is in that is moving. All the radars I've talked about before. Well, ship-based radars, they're moving relative to the sea, but it's not that much, just 30 knots. But when you've got an aircraft that's moving at Mach 1 or something approximately Mach 1, you've got a radar on it, there's going to be significant shifts of the Doppler spectrum, because the Doppler that the aircraft sees depends on a lot of things. First is the Doppler of the target, and then the Doppler of the clutter. Now, if the aircraft antenna is pointing its beam straight out, if the plane is moving this way and the aircraft is moving this way, we're going to have a very different Doppler characteristic than if the target is moving away and the plane is going this way. Here, they could potentially be moving at 0 Doppler, but here they're going to be moving at a very, very fast Doppler towards each other. In addition to that, the Doppler frequency of the main beam clutter, that's the clutter in the main beam, depends on the scan direction. If the antenna is looking over tangential to it, the Doppler of the clutter is 0. Whereas if it's moving in the direction that the plane is moving, it's going to have a high Doppler component going one way, or if it's looking backwards, high Doppler component the other way. And these different graphs show you that the relative Doppler of the target, right here with this arrow, when the plane is moving forward, and then that Doppler moves over when the plane is here. Then when it's sideways, the Doppler is 0 because in this case it looks like a missile. It's moving tangentially to the radar, but also the clutter is moving tangentially. So you've got in the ground clutter that's not moving the target, which isn't moving with a radial velocity relative to the target. And then in the back end, you've got the target moving to another place. So you've got the ground clutter moving, and you've also got the target moving, and differently, because the Doppler frequency of the main beam clutter depends on the scan direction, and the Doppler frequency of the target depends on scan direction and the target aspect angle. So it's a very complicated clutter reduction process. Now, if we looked at just in the next two view graphs, this is a graph of the power spectrum of the clutter. We'd see if we have an inbound target and an aircraft which has a radar in its nose and its velocity and it's going in this direction, it sees the target, and the target would have a pretty high Doppler. You'd have this velocity and this velocity. The apparent motion is very fast, so the Doppler would be very high. The radial motion very high. And that's in a clutter-free region. Okay, and then we've got the main beam clutter, where the main beam is hitting the ground and coming back here. And then we've got another bump in clutter where from the side lobes, the side lobe energy will go down, hit the ground, and come back up. And there's a whole area that will contribute in Doppler to clutter in the so-called side lobe clutter. Here we see it, and it extends over these increments of Doppler frequency. Now, if we have the target not inbound but outbound in red, we see that that outbound target's Doppler is in here now, not because if it changed direction, it was going away. It was in a tail chase configuration. And here we see the target competing with the side lobe clutter, which could very well be a significant issue to deal with. So the main point in just these three view graphs I want to put out is that airborne clutter rejection is a lot more complicated and deserves a couple of lectures all by itself. But I just want to point out to you some of the issues as to how ground-based radars are different and what they have to do than airborne radars, and what some of the differences are in a very general sense, because this is an introductory lecture. Now I'm just going to, for one view graph before we end, present to you the concept of displaced phased antenna, DPCA, just to tease you a little bit about one concept, how you could handle clutter in an airborne platform. And let's say we have a big aircraft here, and we have a big phased array radar that's the size of this entire rectangle. And at time t1, the aircraft is located right here. And say, for instance, we illuminate the elements in this half of the antenna, the forward half, and generate a beam, and it looks down for targets in the air, and also our targets on the ground or whatever, but it also has got that ground clutter it's got to cancel out, and it looks down at a patch on the ground. Okay? Now, if the plane moves, it's going, of course, at a certain speed, and let's just say that the plane moves in a time t2 later, so that the back half of the antenna exactly is where physically the front half of the antenna was. So we had so we can generate, using the back half of the antenna, another beam, which in physical space, remember the aircraft's moving, not on space relative to the moving aircraft, but in space relative to, fixed in space relative to the ground, the antenna's in the same place. So if the antenna's in exactly the same place, and the phase center that we sent out the beam, then the clutter, there's no motion of the clutter in the ground, no spread, and we can cancel out the clutter from these two pulses with just a simple two-pulse canceller. Turns out it's a little more complicated than that. But in simple terms, that's how the displaced phase center antenna concept works. We illuminate different elements, different chunks of the antenna to compensate for the motion of the plane. And that causes the clutter return spread that's due to the aircraft motion to not be there and to be canceled out. Neat concept. But of course, how this really works is this is second, third, and fourth order effects. But this first order effect really does a good job, and then you have to really do the very complex engineering to make it really, really work. It has been shown to work quite well. Okay, so let's summarize. We've looked at moving target indicator techniques to reject clutter, Doppler filtering techniques that reject stationary clutter. There's no velocity measurements. Blind speeds are those regions in Doppler space where the targets with that Doppler velocity can't be detected. So if it's a blind speed, if a target's got that Doppler velocity, you're not going to see it. And you can change the PRF between sets of pulses to alleviate the blind speed problem, staggering the PRF. And MTI techniques have a limited capability to suppress rain. I didn't go over that earlier, and that's because rain moves with the wind. So just having a notch at 0 Doppler, got problems there, okay? And pulse Doppler techniques that we then looked at, you can use them to optimally reject all the various forms of radar clutter. They actually make a measurement of the radial velocity of the target. And I showed you one example, the MTD, moving target detector technique, is an example of an optimum Doppler processing and its associated adaptive thresholding. Then we went over ambiguities in range in Doppler, and they can be resolved by transmitting multiple bursts of pulses with different time between pulses, with different pulse repetition frequencies, and that can be all unraveled in a computer. And airborne radars use multiple PRF waveforms to suppress clutter. That complex clutter can be used, and we use in those airborne radars high PRF waveforms and multiple PRF waveforms are the part of that spectrum of pulse waveforms that you're pushed into to use in those radars. That's the end of Lecture 8.